my colleague, Dr. Jonathan Reeder, to talk about biofluid analysis and next generation wearables.
Great, thanks, Pat. So as Pat has mentioned, there's been huge advances in developing electronic systems which can interface with biology for both recording biosignals as well as neuromodulation. And on the left, I'm showing a couple of examples from academic work showing how we can build electronic systems which are soft, flexible, and conformal, where a number of these innovations come from concepts in soft materials, mechanics, and in integrated systems. And as Pat has mentioned, there's been huge successes in developing electronic systems for providing new forms of both diagnostics and therapeutics. But electronics are just a single pathway with which you can interface with biology. You can also think about biology as a system of fluid flows and thermal gradients, and both of which present new opportunities for, again, diagnostics and therapeutics. And so my research in particular is interested in developing fluidic systems which can exploit some of these same concepts which have enabled biointegrated electronics to integrate fluidic microsystems, in particular for doing biochemical analysis. And this is distinct from biophysical analysis, which is typically done with electronic systems. So in previous work, we've developed soft microfluidic systems which can laminate to the surface of the skin and passively collect sweat as it emerges from the skin. And so these are comprised of elastomers with very high water barrier properties. This is important because we're collecting a liquid which could be in a very dry environment. We want to limit evaporation or the potential for contamination from the environment. We build these microchannels out of these elastomers and then bond them to the surface of the skin using skin-safe adhesive, where laser machined apertures at the center of the adhesive limit where the sweat can be collected from. And so as sweat passes into this inlet, it passes a colorimetric reagent. We can cause a chemical reaction to occur, which can provide a color change in response to some biomarker of interest. And so these will display a color in response to something like electrolyte concentration. And so these systems are exploiting just the natural sweat pressure of sweat glands. But you can imagine that if an athlete were to rehydrate, this information is immediately obsolete. And so what we wanted to do is design a system which could respond to that and be resettable, so that if they were to rehydrate, they could empty the device. We also wanted to develop a feedback system so that if they proceeded to a level of unsafe sweat loss, they would get a notification. And so this is the system that we envisioned. We start with an initially empty device. If the user exercises to an intermediate level of sweat loss and then rehydrate, the device can then be emptied, returned to its initial state. If they are to exit this loop and continue exercising to the point where they have unsafe sweat loss, we wanted to deliver a skin sensation that would alert the user that they need to rehydrate. But to do this, you need active microfluidics. So in previous devices, we're just using the pressure from the sweat gland. And so this work was aimed at building active microfluidic components which could provide manipulation of sweat on the skin. And so in the next slide, I'll go through a few of the microfluidic components that we've developed. I won't go into the details here, but you can think about these components essentially as recapitulating the function of a pipette. So we take what is traditionally a large rigid object, and we can embed it in a soft, flexible device, which can be laminated to the surface of the skin. And these are all strain actuated. So with a simple mechanical motion, well, we can provide suction and valving capabilities in one of these devices. And one of the novelties of these systems is that they can be integrated monolithically. And so on the next slide, you'll see an integrated system which combines channels, chambers, pumps, and valves in a single elastomeric substrate. So sweat enters at the inlet. It proceeds in a serpentine clockwise fashion to fill the device. And then just below that, we have a pump tab, which if the user pulls, they can extract the fluid from the collection channel into the pump tab and ultimately exit the device. We also use some concepts in optics to display to the user a reversible fluid ingress indicator. So on the right, you can see some corner cube retroreflectors and molded in silicone. These present a very white, bright, scattered effect. That's the white color you see in the channels. And critically, as fluid fills these channels, this optical scattering effect is eliminated, and upon extraction of this sweat, we're able to reverse and regenerate this optical signal. In the video, which will come next, you can see one of these systems in action. So there's a small amount of sweat inside the device. With a simple mechanical deformation of part of the device, we can pull that fluid out and essentially act as a pipette, resetting the device back to its initial state. We also wanted to build systems for delivering chemical agents to the surface of the skin as a form of feedback. And so to do that, we built effervescent chemical pumps. And so this is a system which is around the outer radius of the device. In one of these chambers, we have an effervescent tablet. This is essentially the same material as an Alka-Seltzer tablet. And so when it comes into contact with water, you'll see in this video on the right that it rapidly produces a large amount of CO2. And this foam is then stabilized by a surfactant. And we can use this force from this expansion of foam to eject chemostatic agents, which are loaded in this reservoir around the periphery of the device. And so on the next slide, you can see what one of these systems looks like in action. So we have initially an empty device. Fluid begins to enter this chamber, contacts the foam, and it ejects a liquid solution of menthol on the surface of the skin, where this sensation can then be perceived by the individual, and they can then know that they need to rehydrate. And so on the next slide, you'll see a graph. This is an example of how this type of system will be used in an athletic context. So we have devices on an athlete on both forearms, left and right. And what we're doing is we're tracking the fluid loss in both of these devices as well as total body weight loss. So at time 0, the athlete begins to exercise, and we see a corresponding increase in the sweat collected in the devices as well as body weight loss. At time 20 minutes in, the user rehydrates and back to its initial baseline, resets the devices to their initial point, and then begins to re-exercise. At about 40 minutes in, the user reaches about 1% body weight loss, which roughly corresponds with the onset of dehydration. At this point, both of the devices eject their chemostatic payload onto the skin, and a sensation is felt on the surface of the skin so that the user knows that they need to rehydrate.